This
Session of the day.
conference will now be recorded.
I would like to introduce our speaker, Dr. Kailas M. He is a professor in the International School of Photonics in Cochin University of Science and Technology. He did his MSc and MPhil in physics from Maharaja's College and MTech in optoelectronics and laser technology from CUSAT. He joined Cochin University as a lecturer in 2001. He received his PhD in photonics from Cochin University. He was a postdoctoral fellow in University of Texas, USA. He is the recipient of UGC Raman Fellowship for the postdoctoral research in USA. As a visiting scientist at Tampere University of Technology, Finland, and Robert Gordon University, UK. He is a member of Optical Society of America, International Society for Optronics and Photonics, an executive member of Photonics Society of India, and a life member of Indian Association of Physics Teachers. His area of interest includes fiber optics, optoelectronics, and nanophotonics, etc. He has published over 46 peer-reviewed papers in reputed international and national journals and conference proceedings. He was the principal investigator of several Government of Kerala funded projects, as well as projects funded by European Union, India, UK, and Indo-Finnish collaboration. Now, on behalf of Government Model Engineering College, Kochi, let me invite Dr. Kailas M. to deliver his lecture on optical fiber sensors. Over to you, sir.
Thank you. Am I audible? Hello?
Yes, sir. Yes,
okay.
sir.
Okay. Thank you, Model Engineering College and Dr. Laila for giving this opportunity to share some of the works that we are conducting at CUSAT, and also some idea regarding some kind of optical sensors. So I plan to give this topic, that is polymer micro lasers for sensing applications first, and then I will move over to some basic aspects of optical fiber and sensors later. So I understand that there are a lot of participants from other states as well. So with your permission, I would like to introduce my department for 1 or 2 minutes. I belong to International School of Photonics, Cochin University of Science and Technology. The department came into existence in 1995, and we have 2 flagship programs. One is the 5-year integrated MSc in photonics, which is one of a kind in the country. So you have this 5-year integrated program only available in Cochin University in photonics. And we have another program, that is MTech, optoelectronics and laser technology, for which BTech BE students as well as MSc physics and electronics students are eligible to apply. And one speciality is that most of our students are employed abroad. They are employed in R&D institutions all over the world, and we have active MOUs with many institutions within India and outside, and many of our students get opportunity to visit these universities and conduct their research. This is the list of faculty at the department. We are 8 faculty members. Other than this, we have emeritus professors and visiting professors. And we do outreach programs, and that was in a peak during the year 2015 and 16, when the world celebrated the International Year of Light. And with the funding from the Government of Kerala, we developed an optics kit using which you will be able to perform many of the basic experiments at the school level, optics experiments at the school level. And we handed over these kits to many of the rural government schools in Kerala during that period. But we are continuing this outreach program every year, and we are supplying this optics kit to the schools. And coming to the topic today, so I will be talking about the optical microcavities. So it will be interesting, as you know, to store light energy for a later use. So even though it is very difficult, so storing, what I mean is, you can have the light contained in a box or a cavity for some time, so that it will be useful for many applications. So in that sense, it is not a storing, but what we can do is we can elongate the time period over which the light exists in some structures. That is what we can do. But otherwise, storing or slowing the light is very difficult, that we know, unless it is in an ultra cold environment or Bose-Einstein condensate, etc. But there are certain cavities over which you can keep the light getting reflected many times. For example, here, this is a two mirror cavity, which is very common to any laser system. So when we study any laser systems, you have a gain medium and on either side you have two highly reflecting mirrors, so that the light undergoes reflection many times. So the problem with this kind of mirrors is that you cannot ensure the existence of light for a longer period of time. So an ideal optical cavity should confine the light forever. Practically, it is described by the term Q factor. So the quality factor or the Q factor of any cavity, any optical cavity that confine light, is measured in terms of the Q factor. So Q factor is actually something which is proportional to the confinement time. So how long you can confine the light in a specified area. So this kind of optical microcavities, so how can we improve this time or increase this time duration over which the light can be contained? So there are several structures, like the spherical structures, dielectric structures like this, and then this distributed feedback kind of microcavities, and it's a photonic crystal cavity. So I understand that there are other talks on photonic crystals, etc., in this FDP. So you may be learning about photonic cavities and photonic crystals deeper in that talks. So, but the speciality is that this is something that is very common to the lasers, bulk, but these structures are very small, maybe microns in size. So these structures can be a tool to trap the light. Okay, so trap the light so that it can be used as filters, as lasers, sensors, and switches. So you are familiar with the resonance in the, maybe if you are from electronics background, you are familiar with the filters and the resonance systems working in that. So this is a comparison of the Q factor for different biological and man-made resonance systems. And on comparison, we come to know that the microcavities, they offer the largest Q factor. So the optical microcavities are important because they can hold the energy for a longer period of time. So these are, this particular one is a Fabry-Perot microcavity. It is very common in lasers. And the second one is called WGM microcavity. That is called Whispering Gallery Mode microcavity. So we will come in detail for this one later. And this is a distributed feedback microcavity, and this is a photonic crystal microcavity. And this is the Fabry-Perot cavity that we have seen in the last slide. So very common to the lasers. And what is happening here is the light is actually entering through one of the mirrors, partially reflecting mirrors, and it gets into the cavity. It reflects many times, and you can have some kind of filtering effect happening. Only selected frequencies are transmitted, and you can select these frequencies very easily by adjusting the separation between these two mirrors. That is the simplicity of this kind of resonators. So the optical resonator is basically an optical filter. Only certain wavelengths, which are known as the cavity modes, are transmitted. So what is happening here is you have the light reflecting back and forth, and when you have the path length is an integer multiple of the lambda, they will only get constructively interfered, and then they can increase their intensity, and only selected such frequencies will be supported by this cavity, and you can choose the frequencies by simply adjusting the separation between the mirrors. But this kind of cavities, they should offer very high value of the reflectivity. The reflectivity of the mirror should be very high, and in order to contain more light or to have better Q value, it is seen that you have to minimize the size of the cavity. So in many lasers it can be centimeters, but excuse me. So it can be centimeters, but we are talking about micrometers right now, and it is very difficult actually. The reflectivity of these kind of mirrors are basically depends on the coating technology. So you have multi-layer coatings for 100% reflection for a particular wavelength. So that technology is not very cheap. So, and also it is very difficult to maintain the structures in parallel, these two mirrors in parallel, keep the mirrors parallel all the time. So the high reflectivity and shorter cavity length actually leads to better quality factor. So we will learn more about quality factor right now. So these are the frequencies that are selected by the cavity, and the fineness or the sharpness of the frequencies selected are depending on the reflectivity. So if you have an 80% reflectivity, this is the spectrum that you are going to get, and if you have a 40% reflectivity, this is much broader. So how sharper your frequency will be depending on your reflectivity. And also the distance between the selected frequencies, that is controlled by the length, that is a separation, the separation between the mirrors. So these are actually the selected modes, and the separation between them is controlled by the length of the mirrors, I mean the separation between the mirrors. And the Q factor is defined like this, that is the frequency divided by the frequency width. So coming to this special type of modes, which are known as the whispering gallery modes. It has its origination from the St. Paul's Cathedral, London, where you can observe the acoustic resonance. You can see a dome over here. This dome is about 32 meters in diameter. It's a circular gallery under that dome. So even a very small whisper uttered from one side of this gallery is very clearly audible at the other side or the opposite side of the gallery. So what is happening here is the acoustic resonance. So the sound clinging to the walls it is not decaying very fastly, very rapidly. It is actually circulating over here and then coming back to the other side. So it was explained in 1878 by Rayleigh. But later on, it was found that this kind of resonant oscillation is also possible in light, in the case of light. So if you have a spherical structure, dielectric structure, something like this, in 1908, using the Maxwell's equations, the scattering spectra of the plane waves from spherical particles were explained, and these were also named as the whispering gallery modes. So for light also there exists whispering gallery modes. So this is a geometrical optics representation of the light propagation in such a microsphere. This is a sphere. You can imagine something like a sphere made of glass or sphere made of transparent polymer or plastic. So you can confine light in this manner. So the selected frequencies here will depend on the circumference, the length. So those frequencies which obey the condition that the path length, the optical path length is integer multiple of the lambdas, they will be only producing the modes or the required frequencies. And if you simulate the electric field oscillations in such spheres or such structures, it will look like this. So let us see why we should go for a whispering gallery mode resonator rather than a Fabry-Perot kind of resonator. As I mentioned earlier, the alignment of mirrors is very critical. Otherwise, the light energy will very easily escape from the cavity. So usually, even the Fabry-Perot cavity, they don't make use of a perfectly plain mirror. They make use of curved mirrors, but even that is not sufficient for high Q applications, Q value applications. For example, these mirrors are, as I mentioned earlier, they are made by coating technology, multi-layer coating. So you can imagine lambda by 4 thickness of coatings of such different materials over a substrate to produce this kind of mirrors, manufacture this kind of mirrors. It is extremely difficult. So the Fabry-Perot resonators technology is state of the art. Two miniature curved mirrors kept at extreme close proximity in a Fabry-Perot resonator. Here, the Q value is limited by the imperfections in the dielectric coating and substrate polishing. So the polishing of the surface, the imperfections available on the surface of the mirror, so all of them is going to limit the Q value. Scaling to a large scale experiment and widespread low-cost commercial products are unrealistic due to manufacturing complexities. So in any case, the Fabry-Perot cavities cannot generate huge values of Q. These are some of the modern different types of structures which generate whispering gallery modes. For example, this is a whispering gallery mode generated on a disk. You can have toroids, spheres, etc. And this is something different that is photonic crystal based. So let us have a comparison between the Fabry-Perot cavity and WGM cavity. The Fabry-Perot cavity needs to decrease the cavity size, allowing strong light confinement. As we mentioned earlier, the size is very important, size of the cavity. So this separation we have to decrease, and also it needs to increase the reflectivity of the mirrors for reducing optical losses. Q is limited by coating quality, we have mentioned earlier. But here, in the case of WGM, it is low optical losses. So you don't have any mirrors. The surface quality of the sphere will directly determine the quality, the Q factor. So low optical losses, miniature sizes are possible. So you can imagine such spheres of few micrometers, tens of micrometers or hundreds of micrometers very easily you can fabricate. Narrow spectral line widths. The spectrum line width, as we mentioned, the sharpness of the frequencies generated, that is can be very, very narrow. So the resonant condition satisfied is, as I mentioned earlier, the integer multiple of lambda. The path length should be an integer multiple of the lambda. The Q is limited by the surface quality and absorption only. High reflectivity over broad wavelength ranges. Coupling is by evanescent field, analogous to quantum tunneling. So here coupling is not an external coupling. The light is not coupled from the external environment to the lasing cavity through the mirrors. But here the coupling happens something similar to the tunneling. You are familiar with the tunneling effect of the electron. So equivalent to that, the photons can also tunnel into uh, the forbidden regions. So the evanescent field mechanism is used for coupling. So we will see in detail later. So why should we go for such a micro resonator? So if we examine these kind of micron-sized light trapping devices, they offer different functions. So they act as a switch, they can act as a resonator, they can also couple light out, or they can take light from outside. So we know a switch is used for creation, transition, and termination of connections. So in electronics or electricity. So in the same manner, you can make use of a micro resonator as a switch. Let us see, we will see how it is actually happening. So we can input light into such a micro resonator at certain conditions. And what is a resonator? A resonator reinforces a frequency. So it actually selects frequency and also optical coupling. So light can be leaked out of a cavity, or you can couple light into the cavity from external world. So this is something similar to the directional coupler. So if you have studied about the optical communication, you have a directional coupler, so which makes use of the evanescent field that is penetrating into the nearby waveguide. So for example, you have a waveguide here 1 and waveguide 2, and you have two cores of the fibers. These are sitting very close to each other. So you can imagine something like an uncladded fiber. This one, the waveguide 1, the uncladded fiber 2. So the fiber cores are very close to each other. So even if you are giving input to one of the amps, so the light can very well penetrate into the second fiber or second waveguide, and depending on the coupling conditions, for example, the proximity of the two fibers and how long, up to what length you are keeping this proximity, so you can split the light to 50-50 or 10-90 or whatever proportions that you want. So that is the function of a directional coupler. So similar to that, you can also couple light out of or into a micro resonator. So if you are familiar with the optical communication, you might have studied about the add drop multiplexers, optical add drop multiplexer. So this is actually a combination of a fiber Bragg grating a circulator, and this is the input fiber and this is the output fiber. So this system, add drop multiplexer, it takes a number of channels as the input, and it can drop one of the channels from here. So because there is an FBG, the periodicity of this FBG is arranged or adjusted in such a way that it actually acts as a filter for only one of the wavelength. Okay, and circulator is a unidirectional device, a 3-port device. So whatever input that you give, so it is a unidirectional device, and also it will come out it will exit through the very next port. So here you have one channel that is dropped from here and another channel that is actually added. So it can add, so you have to adjust the FBG, this side, the FBG, so that it can accommodate this particular wavelength. So one channel is dropped here and one channel is added here. So this is a very complex mechanism, that is, it contains optical circulators, FBGs, and it is a full package that is giving you add drop multiplexing. But here, our micro resonator, suppose this is a micro sphere that contains light, which can tap light, which can trap light, and these are two optical fibers sitting very close to the microsphere. So the similar function can be performed by a microsphere and two fiber combinations. Something like this, you can drop a particular lambda, because this lambda will be coupled into the sphere depending on the conditions that are provided, the coupling conditions. And you can also add another channel from here, from the second fiber, and it can be added to the original fiber, the first fiber. So this function of add drop multiplexer can be very well performed using a microsphere optical fiber combination. Similarly, it can be very well used for sensing, especially in the case of biological samples. So you can have this is something like a optical fiber. Tip of the optical fiber is heated, and it becomes a sphere. Okay, so due to the surface tension, this melted glass, it forms the shape of a sphere, and this is an optical fiber. This is an optical fiber, and this is a source and a detector, and in between, the fiber is actually tapered. This is not a normal fiber. The fiber is heated and pulled so that the diameter becomes lower. And the importance of this is that whenever you change the diameter to a lower side, reduce the diameter, the electromagnetic field contained in the mode, it actually comes out of the fiber. So it can be very easily coupled into this sphere. So in that way, this sphere can be functionalized also. In many of the biological experiments, you coat this material, which is called the functionalization of this sphere, and you can attach antigens or some special analytes into this functionalized region, so that the refractive index of this region can be affected. So with the presence of the analyte and without the presence of analyte, what you're going to find here is a dip in the transmission spectrum. So this is a transmission spectrum. So a one specific wavelength will be dropped from here, and that wavelength will be shifted to some other wavelength once you have a change in this environment. So this is a very good sensing application, especially in the case of biological samples. So this is an example of such a micro cavity and two optical fiber combination, two optical fibers and a micro cavity. So you can, depending on the conditions, you can couple certain frequency into the sphere, and also you can remove that by adjusting the coupling conditions over here. So in the same manner, you will be able to add new channel from here. So this is very well possible with this kind of micro resonator. So an optical ring resonator can redirect light. So this is called a ring resonator. Even though this is shown as a sphere, this is a ring. There are many structures possible. Specific frequencies get redirected. That means it filters them. The size changes with thermal expansion. So you can adjust the conditions over here, which frequency have to be coupled out or coupled in. So that can be adjusted. So WGM resonators are basically monolithic circular dielectric structures. So WGM resonators rely on total internal reflection rather than dielectric mirrors. Okay, so the Q is determined by the surface quality and absorption, not limited by the coating quality. So the coating technology is not coming into picture. High reflectivity over a broad range of wavelengths. Coupling to and from a resonant mode is achieved via external evanescent field at the point of total internal reflection, analogous to quantum tunneling that we mentioned earlier. Tunable strength, high reflectivity. So the strength can be tuned, and these are various structures possible. The sphere can be a cylinder, it can be a ring fiber combination or a ring disc combination, and this can be a toroid. This has huge applications in sensing as well as in biology, because we have seen that the microspheres, they offer the largest value of quality factors. The Q factors are much bigger for them compared to other structures, and at the same time, more interestingly, it is most easier to fabricate the spheres than any other structures. So the quality factors of 10 raised to 8, 10 raised to 9 can be obtained from different liquid droplets. So this can act as active sensors for biosamples. So the liquid droplets are generated, and in this particular experiment, it is actually levitated and it is actually kept stationary here, and it is shined using a light. The laser actually generated the frequencies generated in the trapped in the sphere in the liquid droplet can be analyzed using a CCD camera. So this is the figure, the image of the droplet which is levitated. So the interesting thing is that the sphere can also contain some gain medium, just like the gain media that we talk about in lasers. You can dop this liquid. So the liquid droplet will contain the gain medium, which can be excited by the incoming light, and the emission from the gain medium will be trapped, and those frequencies of emission coming out of the gain medium will be trapped inside the sphere, and it can be very well imaged. So there are many micro droplets containing CDSE, ZNS, nanocrystals, or quantum dots. So you can dop quantum dots into this liquid and form a droplet and then suspend it and then study it. Silica-based WGM resonators. So the most of the studies that is available are based on glass resonators or silica-based WGM resonators. The majority of solid WGM resonators are made of silica that is in a spherical shape, mostly by melting fiber tapers. So you have optical fibers readily available from the market, and you can melt the tip of that fiber so that it forms something like this, a spherical shape. And this can be very well used for, as I mentioned earlier, this structure offers the maximum Q factor, and it is also most easier to fabricate this kind of spherical structures. So due to the surface tension, the melted part of the silica fiber taper transforms into a microsphere. But these are more complicated structures which requires much technological assistance to fabricate. Okay, it is a microsphere, then a microfiber, microtoroid, capillary, microdisc, split disc, microbottle, and ring resonator. But what is interesting, but one thing I have to mention here, the silica, the silica based technology is very expensive and very complex, just because it requires around 2000 degrees Celsius to melt this kind of silica based optical fibers or structures, and controlling the process at 2000 degree is also even rather difficult. But coming to polymer or plastic based WGM resonators, you have many advantages. Something like they are more flexible, they are more cheap, and very less expensive. The technology is very less expensive. And this particular figure shows micro goblet lasers fabricated by parallel solution based processing. So you can see a periodic arrangement of different micro lasers by this process, solution based processing. So new processing techniques and the low cost and elastic nature of polymers are very much used in this technology. And you can have a comparison between the properties, the material properties of PMMA, that is polymethyl methacrylate. It is a transparent polymer, transparent plastic used for this kind of applications, and the common silica. So here, what is shown here is two coupled lasers, coupled fibers. So this is a fiber and this is another fiber. So the field can be coupled from one of the fiber to the next fiber. So this is basically the cross section of the fiber. It's a larger diameter fiber and a smaller diameter fiber. They are sitting very close to each other. So you can couple the laser from one fiber to the next fiber. And this is lasing spectrum. So you measure the spectrum, you can see it is very narrow, and this is the actual photograph of the two coupled fibers, the larger diameter, smaller diameter. So we have seen it is very easy to work with the polymers rather than the silica. So the polymer is an ideal choice for an optical integration platform. It is low cost, it can be easily manipulated. There are different techniques like embossing, stamping, sewing, etching, etc. The thermo-optic coefficient is 10 to 40 times larger than that in silica. If you compare the thermo-optic properties, it is very easy to work with this kind of materials. But one disadvantage usually people show is the best quality PMMA has lost 55 dB per kilometer. So this is quite unusual for optical communication experts. So we usually work with the silica fibers, which offers 0.1 dB or 0.2 dB per kilometer. But this is very, very huge. But still, this can be used for very short length applications and applications like sensing, making lasers, and this kind of microstructures. It is very easy to fabricate, and mainly the low processing temperature. The processing temperature is almost 10 times lower. Compared to the 2000 degree, here it is only 200 degrees Celsius that is required. And compared to the silica fiber, the diameters are much larger. And you can have fibers of diameter 1 millimeter, 900 micrometers, 700 micrometers. They are very common. But compared to the silica fiber, which has a core diameter of 10 micrometer approximately. So very difficult to handle, couple, and etc. Very expensive as well. But one figure you have to remember here is this one. This is the loss spectrum or the transmission loss versus wavelength diagram for PMMA. So this offers something like a minimum loss around 650. So we are familiar with the transmission loss diagram for silica fibers. So we know that the silica fiber offers minimum transmission loss around 1550. So that is in the infrared, but you are dealing with the visible light here. So if you have some applications which makes use of the visible light, you can very well use the polymer material. And obviously the general benefits of all other optical fibers are relevant here as well. But you have to remember the values I have written here is applicable to the common silica communication optical fibers. But the other advantages of optical fibers still remain with the plastic optical fibers. So with this background, we started fabricating this kind of structures using plastic, basically PMMA. So these are the PMMAs, I mean the methyl methacrylate in solution form that was doped with different fluorescent materials. So you can see different colors starting from pink to green. You can have combinations of these organic dyes doped into this material, and then they can be solidified and they can be pumped with a laser, and you can expect more than one wavelengths coming out of this kind of structures, and even multi-color lacing is possible from this kind of materials. So for example, I have a solid plastic medium which is doped with a fluorescent material. Then I am pumping this with a blue laser. I can expect a green emission as well as a red emission. So that can be confirmed from here. So you can have many combinations of fluorescent materials, and it is very easy to dope such materials, and not only the fluorescent organic dyes, but also the nanoparticles, quantum dots, metal nanoparticles. So there are so many dopants that can be very easily accommodated into these kind of structures. And another one important thing is it is not just filling a glass tube and then solidifying it, but here we have done something different, that is the graded index structures also fabricated. So if you remember the optical fiber characteristics, two important characteristics are the attenuation and the dispersion. So attenuation means the signal level goes down, and the dispersion means the pulses spread in time. So this is a very famous cartoon which depicts attenuation and dispersion. So that means two tall and lean people are crossing a tunnel, and while coming out, these people become very short and fat. They become short because of the attenuation, and they become fat because of the dispersion. And this is very common in optical fibers, and even in single mode fibers you cannot avoid this kind of attenuation and dispersion. But in multi-mode fibers you have a larger diameter of the fiber and you have many modes traveling together. So in that case, it is always advisable to use a graded index structure. So in this figure, you see the step index profile. This is smaller index in the cladding and the larger index in the core. So, but this is a step function. But if this is a graded index fiber, so this will be the structure, or this variation can be parabolic or something very close to that kind of variation. So you have a certain value of refractive index for the cladding, and for the core, the maximum refractive index will be at the axis and it gradually decreases. So this is a multi-mode step index, this is a multi-mode graded index, and this is a single mode step index fiber. And this is the one that is most commonly used in optical communication. But if you want to use a multi-mode fiber, it is always advisable to make use of a graded index structure. So we tried a graded index structure over here. So you can see this photograph. It shows that on the sides it is transparent and at the middle it is a pink. So that means the pink color is the fluorescent material that is added. That is the gain medium. So what is happening here is you start with a hollow polymer tube. You initially make a hollow polymer tube and then fill that tube with the monomer again, that is the methyl methacrylate, which after solidification becomes the plastic or the solid. So you start with a solid tube-like structure, then fill this inner region, fill that tube with the solution. That solution contains the monomer, that is the monomer is A, which are smaller in size, which will obviously solidify after some time when you apply external energy, usually heat. But this B is something different. It's a different kind of molecule which can improve or enhance the refractive index. So this material as a combination is filled in and then it is heated. This is a cross section of the tube. So the solidification actually starts from the side because the heat is actually coming from the side. So this A becomes solid initially because they are very smaller, and this region becomes somewhat gel-like because this is solid and this is liquid, and in between it has to be something like a gel form before it is being completely solidified. So this A being smaller in size, they will penetrate more towards the outside and they will get solidified very easily. And finally, you will have these molecules B, which are bigger in size, aligned along the center, or maximum concentration of B's will be along the center, and you will result in a, and that will result in a structure something like this. You have a cladding and you have a core which is having a refractive index which is continuously changing and maximizes at the axis. So this process is actually called interfacial gel polymerization. So you can see a rod that is polymerized accordingly. And we can confirm that this kind of plastic that is made is really, its refractive index is graded index. So one experiment that can be performed to characterize this kind of plastic rod, graded index rod, is that this Mach-Zehnder interferometry. So wherein you have a very thin slice of the plastic rod kept in one of the amps of this Mach-Zehnder interferometer and then record the pattern, the interference pattern, using a high resolution camera. So you will find this kind of variations, bendings in the fringe pattern, and from the bending you can calculate how much index difference has happened within the core region compared to that in the cladding. So this is a method that is used for the refractive index profile measurements in this kind of roads. And this is about the calculation, the regular graded index theory. So what we have performed is that initially we performed an experiment based on two different fluorescent materials doped into that structures. So this is a common step index fiber, and this is a graded index fiber, something like you can see when external light source is applied, or we can call it as a pumping. External pumping is applied to such a fiber. This is a fiber piece, and this is a laser, Indiag laser 532 nanometer. This is focused onto the fiber, and you can see there is a amplified spontaneous emission. Originally, the spectrum was very wide with lower pump energies, but when the pump energy increases, this becomes narrower. And this is all for the step index kind of fibers doped with rhodamin 6G, one organic dye. This is rhodamin B, another organic dye, slightly different in color. And this is a combination of both rhodamin 6G and rhodamin B. And what is interesting to note here is that this is a graded index structure, similar in diameter in all other dimensions. Here, a rhodamin 6G doped graded index fiber, and this is a rhodamin B doped graded index fiber, and this graded index fiber is doped with a combination of these two. So what is interesting here is the graded index structure actually generates lacing. So a step index structure was not lacing, it was not getting converted into a laser, it was simply narrowing its emission region, but here it started lacing. One important type of fiber that is being studied worldwide right now is the photonic crystal fibers. So it is a entirely different class of fiber which makes use of or combines the properties of two-dimensional photonic crystals and classical fibers. So they are the fibers which have holes running along the length of the fiber, and these holes are arranged periodically. So you can imagine this as a glass rod, and multiple number of holes are drilled from one length to the other, the one end to the other end of the fiber, and these are periodically arranged. So this is something similar to an electronic crystal, wherein the electron will find a band gap while propagating from one point to the other point, just similar to the electronic band gap. The photons, while passing through such devices, they find forbidden regions, forbidden energies. So what happens here is, this is the direction of photonic band gap, means that when the light tries to propagate along this direction, it is forbidden. Along this direction, it is also forbidden depending on the periodicity. But this is a region where you don't have any hole. So this is something like a defect in the crystal. So you have deliberately avoided a hole in the middle. So that means this can act as a core of the optical fiber. And one important thing to be noticed here is that this is simply a glass rod with air holes, and you doesn't require the core and the cladding fabricated separately. So from the same material, simply by drilling the holes, you can have the optical fiber with you. So this is one way of transmission through photonic crystal fibers. And the other way is to have a hollow region. This is also a crystal defect, and this can be also regarded as a defect. something like this is a photonic crystal structure, and this is a region over which you can have a defect. That means this is a hollow region. So since the light is forbidden here, the light should pass through this hollow region. So this is extremely useful for transporting huge amounts of energy from one point to the other. And one important property of such fibers is that they can be endlessly single mode. They can be single mode. They can act as a single mode fiber for a wide range of wavelengths, which is not applicable to the common optical fibers used today for communication. So we know the whether a fiber is a single mode or a multi-mode will entirely depend on the wavelength of operation, its geometry, the values of refractive indices of N1 and N2. So, but here you can have a variable value of the core, the cladding refractive index. The core refractive index, while remaining the same, the cladding refractive index can be, continuously varied in accordance with the change in lambda, so that it will accommodate the changes in the V parameter, so that the light will continue to be in the single mode, or the operation will continue to be in the single mode regime. But here I want to mention here that we also tried to make a plastic-based, polymer-based photonic crystal fiber, and it was a failure. So you can see a cross-sectional view of the photonic crystal fiber that we tried in CuSat. These are taken from the literature, and also these are basically silica-based fibers, and this is a plastic based fiber for the PMMA based photonic structure. And you can see that many of the holes, they have merged and the periodicity is broken. And so what kind of technique that we have used here is we initially fabricated hollow fibers, the fibers with a hole. A large number of them were stacked inside a bigger tube, and then that was drawn. But even though it was a failure, so we started working on this hollow kind of fibers, and we found that these hollow optical fibers, when doped with some fluorescent gain medium, they can very well act as micro lasers, or the micro cavities, the WGM micro cavities that we have been mentioning for some time. So so these holes, each of these holes were derived from different hollow optical fibers filled within a bigger tube before drawing. So we started working on that kind of hollow structures. You can see a hole here. This is a hollow optical fiber. And the micro ring cavity, polymer micro ring cavity, was originally reported in 1996. And the cavity structure was something like this. This is a polymer, fluorescent polymer. And then you have two mirrors, and it was excited using a 355 nanometer light, and it was emitting around in between 500 to 600 nanometer. And it was a it was a structure with very high value of gain. And they predicted that even thresholdless lacing is possible from this kind of structures by adjusting the mirrors and the materials and the thickness and all. So that means this thickness is only lambda by 2 thick. So you what they suggest is that these kind of structures will have very low threshold pumping requirement. So the external pumping required for emitting a laser is very, very small. And another kind of structure that is already reported is, this is a glass fiber and this is a polymer coating. So take a glass fiber and making a coating, and if this coating contains a gain medium, and then you make an external pumping of this gain medium. So this can act as a laser. So obviously there is no mirror. So the circular structure act as a mirror, and it can act as a very good high quality micro cavity, or if it is having a gain medium, it can act as a laser as well. So this is a photograph of the hollow optical fiber. So if you take a cross section of such a hollow optical fiber, it will look like this. Why this is red? Because this is doped with a fluorescent material. You can see a clear distinction between the light paths taken in these two structures. So one is going to the inner boundary, coming to the external boundary, and this repeats. And whenever this path length is an integer multiple of lambda, those frequencies will be circulating. But here you have remember that this is a cross section. So here the polymer layer thickness is somewhat larger. So in this case, this reflection cannot reach the inner boundary, but it circulates something like this. So this is exactly what is the wave, the whispering gallery mode that we were mentioning in the case of acoustic waves in the cathedral. So this is something like in an optical fiber, normal optical fiber. So total internal reflection. So these are actually known as the waveguide modes, and these are the whispering gallery modes. Both are WGM. This is waveguided mode, and this is whispering gallery mode. And the frequency selection, you have different frequencies selected, and you have separation between them. And this delta lambda, the lambda separation between any two lambdas selected, is simply given by lambda square divided by pi d np. Np is the refractive index of the polymer, and d is the diameter of the structure. So this is this is a cross section. You have to remember that. So what we see from here is that in a thick film, the modes never reach the inner polymer air interface, and it is confined by the total internal reflections at the outer air polymer interface. Okay. So you can pump these kind of structures, and you can make lasers out of that, and these are the some of the frequencies selections. It is not lasing, but it is beyond the ASC stage. If you give enough pump power, it can act as very good lasers. So these kind of structures with holes inside, for example, the hollow waveguide. This hollow waveguide, if you dock with, for example, this is a sensing gas flow sensing device, which makes use of such a silica based fiber. This silica is doped with erbium ytterbium combination. So erbium ytterbium doped silica fiber, and this is having a hole, and through the hole a fluid is actually flowing, and the excitation of the WGM is represented by these red arrows. So you have a fiber here. So if you couple light through this fiber into this cavity, that is, this cavity is made of silica, that is erbium ytterbium doped silica, and the slight heating of this cavity by the absorption of light over this here can change the diameter. So that change in diameter will be measured in terms of the shift in the frequency. So you have light propagating from here through the fiber, and it is continuously monitored here at the output, and you will have a dip corresponding to the light that is coupled to the cavity. And once it is heated, the fluid flow will be different because of the change in diameter. That can be very easily monitored by this shift in the uh, frequency. So the shift in frequency is basically due to the temperature variation, but it is actually a measure of the volume of liquid that is flowing through the capillary. So there are different coupling techniques available for this process. How you can couple light uh, to a cavity. So it can be a free wave coupling. So something like you shine light from outside directly onto the structure. That is called the free wave coupling. Or it can be evanescent coupling. You can use a tapered optical fiber, something like this. This is a source and this optical fiber. This is tapered region. And very close to the tapered region, you keep this, polymer fiber or microsphere or micro disc, whatever structure, so that a particular frequency or particular wavelength will be coupled into the structure. And the frequencies that are coupled here into this structure, micro cavities, will be missing in the output spectrum. This is an optical spectrum analyzer, which plots the wavelength versus transmission. So here you will find that some of the frequencies are missing. So those missing frequencies are basically coupled to this micro cavity. So that kind of coupling is called evanescent coupling. So we allow the field, the evanescent field in the fiber to come out easily by tapering it, because reducing the dimension will enhance the evanescent coupling. That means the energy leaking from the waveguide structure. So we know this parameter FSR, free spectral range, that is the separation between the wavelengths that are selected. So we have already discussed this, and this is also discussed, that is the Q factor. These are the two important parameters. So if your delta lambda is very small, you have a high Q value. The polarization can be transverse electric and transverse magnetic. The coupled electric field oscillations, you can study them, you can plot them, and you can number them actually by using the asymptotic equation. You can number the order of the modes in terms of the radial mode or the azimuthal mode number or the radial mode number, which order of the mode is actually currently oscillating. That can be easily plotted. So this is a passive WGM resonator based sensor. Passive means this is the fiber, and this simply couples light into the cavity. The cavity does not act as a laser. It simply couples light from here to here. Okay, it cannot emit any laser. So this is a COMSOL simulation. So no use of the gain medium. So it is not doped with any organic substance. High power laser source is not involved. No photo bleaching. So one of the important problem that we face, that we will discuss later, is the photo bleaching or the degradation of the whatever material that is doped into the cavity. But in this particular case, nothing is doped. That is, it can simply tap or trap some frequencies while kept very close to the other waveguide. So this is a sensor fabricated using such a structure, that is a fiber which is doped with rhodamine, polymer fiber doped with rhodamine, and this is an active temperature sensor. It is called an active temperature sensor because the light is actually used to pump the fiber, and the fiber is having a gain medium because it is already doped with the fluorescent material. So it emits light, and that emission is a laser, because this surface acts as the cross-sectional, the surface, cylindrical surface of the fiber enables it to, efficient recirculation, and it promotes the resonance, and the frequencies are monitored accordingly. And this chamber is actually heated so that there can be variations in the temperature variations can cause some variations in the diameter or some variations in the refractive index of the material. That is possible. So accordingly, the frequencies can shift, because we know it depends on the diameter. The frequency selection very crucially depends on the diameter. So by temperature, applying temperature, it can vary. But here it is a passive WGM sensor. For example, the fiber, this is the light containing fiber, that is a superluminescent diode is used to couple light, and this is fiber is tapered over here, and it is given to the optical spectrum analyzer, and this is a coupling region, and across that coupling region or the tapered region you have a microcavity, cylindrical microcavity, which is not at all doped. So the transmission spectrum alone can be studied to monitor some parameter which can act as a sensor. So this is basically a comparison between active and passive sensors. One interesting thing to be noticed is that you can have interference between the waveguide modes and the whispering gallery modes. That can lead to some kind of modulation. That we have said earlier, entire thing depends on the thickness of the film. So this is a cross section of the hollow structure, and if thickness is more, you have only WGMs, that is the whispering gallery modes, and if the thickness is smaller, you have the usual wave guiding modes. That is something similar to the normal TIR happening in optical fibers. So at certain point, you see that a combination of these two happens, those two different sets of frequencies oscillating simultaneously, and that can cause some kind of modulation behavior, the two sets of frequencies oscillating together. So one interesting structure that we tried here is that a micro ring embedded hollow fiber. I mean, you have a hollow structure, something like this is a same image of such a material, such a micro cavity, and the inside region of this inner wall of this tube is coated with a gain medium. This is expanded view. So this is the cross section, and only a very thin layer of gain medium is coated in the inner wall of the tube. This is a structure, and it was pumped, and this is a fiber. It was pumped transversely, that is from the side, and the spectrum was analyzed, and these are the experimental parameters used. We obtained a Q factor like 6 into 10 raised to 3, and a free spectral range of like 0.378 nanometer, and full width at half maximum of a single peak, which is 0.09 nanometer, and we were using a pump energy of about 2 millijoule. So for this was a pulsed laser excitation. This is an India laser. So a laser was used with a pump pulse energy, so 2 millijoule. So we were getting this kind of highly modulated peaks. So the frequency selection was extremely good in this kind of structures compared to the normal hollow fibers or solid fibers, wherein you have complete doping. So this entire region will be doped with the fluorescent material, but this is a very thin layer. So the result was something like this: a single mode operation was possible. So you have only one frequency oscillating, and all others are suppressed. So the mechanism working over here is that the normal WGM is modified into two WGMs, which are modified WGMs. You can see this point from here. For example, it is getting splitted into, from this point, some part of the light is actually getting reflected and it comes back to this point B, but the other one is getting refracted and it reaching the point D. So from point A to D, you have either by this reflection or through this refraction. So depending on the difference in values of these optical lengths, like N2AB times 2 minus N1AC. N1 is the refractive index of this region and N2 that of the outer region. So depending on this condition, only very selected frequencies are allowed to constructively interfere, and all other wavelengths were suppressed completely, and it resulted in a single mode operation. So this is a photograph of the laser that is coming out of such a hollow fiber, and it was really interesting to see that this was actually collimated to the wall about 1.5 meter distance. So from the laser, from the fiber, we were able to collimate it to a longer distance, even though power was extremely small because all other modes were suppressed, and the energy of this particular mode alone can be very extremely feeble. So the result is that you can have high frequency selection from this kind of spatial structures, that is micro ring embedding inside. So this is the actual photograph of the fiber underlacing. So you can see the inner region alone is generating laser and it is glowing. The outer region is just transmitting some light, but it is not at all a laser. This is simply the light that is spreading over here. So by compromising on the total power, we have accomplished a single mode operation from this kind of optical fibers. Now about the refractive index sensing using die-doped micro ring embedded hollow polymer optical fiber. So these kind of fibers were further used for sensing. So as we mentioned earlier, in the case of a ytterbium doped silica hollow fiber, they were using it as a flow sensor anemometry. But here we are using this hollow structure, which is a micro ring embedded structure for refractive index sensing. So for that purpose, different materials were filled in this region, and the fiber was pumped with 532 nanometer, and the modulated lacing peaks from the micro ring embedded hollow polymer fiber showed a linear redshift with increase in refractive index. So the refractive index was changed, and by supplying different liquids, and the results indicate that the micro ring embedded the refractive index sensitivity of 188 nanometer per refractive index unit was obtained for this kind of fibers. The result indicate the micro ring embedded hollow polymer fiber can be a promising component for active refractive index measurement in many physical and biological WGM sensors. So these selected frequencies that will be shifting with respect to the surrounding refractive index. That is actually what is happening here. So can we tune the WGMs using by applying a strain? For example, you have this hollow polymer optical fiber, the same image of that, and a strain is applied. This is the fiber piece, and a strain is applied in this direction so that the diameter can be varied, and the spectrum was continuously monitored. And you can see that there is a shift in the spectrum. If you follow a particular peak, you have to follow a particular peak in the spectrum from the spectrometer, and you can note the variations in the shift or the shift in the peaks. So that can be used for sensing strain. And the shift in the wavelength in this particular case can be due to a change in the diameter of the fiber, or it can be a change in the refractive index. Okay, so but there is not much change in the refractive index compared to a change in the diameter. So the change in diameter can be expressed in terms of this Poisson's ratio and the tensile strain. So the plugging in the values for these, you can calculate the delta lambda, that is the shift in the lambdas possible by this experiment. That is, the strain sensitivity is calculated to be around 2.35 picometer per microstrain. So this is the cross section of the fiber that is used here, and this is the side view of the fiber, and this is how the shift in the peaks are monitored continuously. So this is the thermo-optic tuning. So with temperature also, a hollow fiber can shift its emission frequencies, emission wavelengths. So that is explained by this diagram. So you have a hollow fiber sitting inside this chamber, and this can be heated, and you have a temperature sensing control coming out of the cavity, and the output spectrum is monitored using a CCD spectrometer, and the fiber was pumped using an Nd:YAG laser 532 nanometer. And the shift in the spectrum is calculated using this equation. So it can be a change in the refractive index due to the change in temperature, or it can be a change in the diameter due to the change in temperature. So you have two coefficients. One is the thermo-optic coefficient, and the other one is the thermo-expansion coefficient, the thermo-optic coefficient. So, but the thermo-optic coefficient is much larger than the thermo-expansion coefficient in the case of this PMMA dielectric. So, the lasing peak at this particular wavelength with a Q factor of 7.5 into 10 raised to 3 was selected for tracking the shift in the mode in this tuning experiment, and the sensitivity was 0.011 nanometer per degree Celsius, and the tuning range obtained was about 0.44 nanometer, so which is almost double the free spectral range. So so almost double the free spectral range. The system can be tuned, and the temperature can be applied, and also it was found that it is purely reversible. This mechanism is reversible. You can decrease the temperature, and it follows exactly the same pattern. Tunable amplified spontaneous emission. So now we talk about simple amplified spontaneous emission, not the laser.
Sorry to interrupt you, sir.
Hello?
Hello. Sorry to interrupt you, sir. We will have a short break at 11:30. Ippo 11:27.
Okay, then we will break. Okay.
The same session will be continued at 11:45.
Okay. Okay. Thank you.
Dear participants, we will have a short break now, and the same session will be resumed at 11:45. So we can leave and rejoin the session at 11:45.